Hello, I'm Skip Brown. This is our third video on motor controls. I felt like we moved along pretty quick on the first two, so let's just drop back for a minute and look at some conventions before we get into the more specific applications. We showed this would be number 1 or X1. Okay, this of course is the control transformer secondary. We come over here to XO or X2, XO, X2, and remember, we always have the capability to make it a grounded system by actually bonding this side of the transformer, and we make it a typical separately derived system. We ground it, but later on in our discussions we'll talk about why we have grounded and non-grounded control systems. So for conventions, last time we used a straightforward stop, start, auxiliary, and a motor winding with normally closed overloads. One of the things we hit on pretty quickly was the concept of two items here. We have NO and NC, very, very commonly used in control, let's say nomenclature, jargon, what have you. So NO doesn't mean no, doesn't mean you can't, doesn't deny you permission. NO means normally open. And NC, yeah, you're right, normally closed. Normally open is the state that a contact is in when the circuit is de-energized. When nothing's happening, when there's no power to the circuit, the relay contacts or button contacts or whatever that don't make contact, those are normally open. Conversely, the contacts that are closed in a de-energized state are these contacts right here, for instance, normally closed. Okay, the other thing we want to talk about is the numbering. Of course, we talked about left to right, okay, an important convention. And then, of course, overloads, these are safeties. And we talked about two types of inputs for controls. So we have series, and we use series for safeties. And we use parallel inputs for starts. So if you recall last time, we had a series of, I shouldn't say a series, a stack of start buttons. We wired them in parallel. They could start the motor. But if we wanted safeties, we had to wire those in series. As an example, what good would a safety circuit be if the contacts were wired in parallel? I push one stop button, the circuit still continues. It's not going to work. So we always put our safeties in series. And the safety doesn't have to be a button. A safety could be a switch, could be a limit switch, could be something tied to a pull cord, anything that we want to stop a motor, whether as routine or in an emergency. So they have to be wired in series. Okay. Next item we want to look at is indicating lights, another convention, indicating lights. Everybody on their control panels wants to know if the motor's running or not. And a lot of times, the button that starts the motor starts a motor remote from the start button and shows up, the light shows up in a control room, also remote from the starter and from the start button. So we want to know wherever the control room is that the motor is running or that it's not running okay? And we want to have this indication be relatively reliable. Way to do that. Now I can always, this is my motor. This contact here is going to be labeled M1 because that's the motor contact. This is my stop button. This is my start button. Now I could always take my light, as we did in the last lesson. I could take the light and put it in parallel with the motor, but that's always not the best way to do it. Not always the best way to do it. What I can do is I can have indicating lights normally open and normally closed. Okay, so here I have two lights, and I want one of these lights to come on when the motor is not running. I want it to be a safety. So what I'm going to do is I'm going to make that a normally closed contact off of the motor starter M1. So this, unlike this contact on the motor starter that's normally open, this one's going to be normally closed. That means that when the motor's de-energized, this light is on. So we can call it an off light or a safe light, whatever we want to call it. Okay? Conversely, this, also an M1 contact, would be my run light. Okay? Run light could be red, and the off light could be green. And the reason we have the run light as red is to tell people, you know, keep back, be careful, the light is running. Green, it's okay, the motor's not running for whatever reason. If you need to do any kind of maintenance or load product or whatever you're doing, the motor is not running. Okay? So those are two conventions for indicating lights. Okay? And I can have other indicating lights here. By putting them on a separate rung, it makes them isolated from any of the overload contacts. Okay? So that's indicating lights. Let's talk about when we want to jog a motor. Okay? Another thing that we can actually have is we can have a need to jog a motor. When we jog a motor, instead of starting the motor at full speed for maintenance purposes and such, we might just be doing some maintenance on the motor, and we might just want to bump the motor, maybe to set up timing, to put a belt on, and so forth. So in that case, we need a run jog switch. This is going to be with or without indicating lights. So what we're going to do is, in order to jog, we have our auxiliary contacts right here. Okay. And we're going to have a selector switch, and the selector switch is going to say run or jog. Now when we do a selector switch, we usually show the selector switch in one or two positions. So this selector switch here is going to be in this position, and I'm going to have two sets of contacts. Okay? One of them is going to be run, like so, and the other one is going to be jog. Now in the run position, I continue this rung, I hit the start button, okay, and the motor's going to energize and latch in, same as it normally would. When I go to the jog position, I'm disabling this. I could actually say that I'm going to move this so it doesn't make contact. Another way to draw it. So in the run position, I'm engaged. In the jog position, I've opened up this rung. It's no longer working. So I have no contact between my auxiliary contacts and my motor starter. Now, in the jog position, this is going to be open. I hit the start button, the motor only bumps while I'm holding the start button down. Okay, the run jog switch disables the ability for the motor to latch. These are called latching contacts, auxiliary contacts, holding contacts. They don't get to latch up. So when I hit the button, yeah, they close, but when I release the button, if this circuit is open, they don't lock. Okay, so that's a run jog switch. It's another convention. Pretty common with motor controls. Let me think of another one. Sometimes we'll have one motor has to be running before another motor can start. This will be another convention. We don't need a run jog in this demonstration. What we need are two motors. And if you want to use your imagination and think about where this application might happen, you might have a piece of equipment that needs oiling. In other words, it needs an oil bath to operate, like maybe a drilling machine or a heavy piece of equipment. So when I start the equipment, I don't necessarily start, let's say my big motor. Okay, let's say M2, which might be the lathe. M1 is an oiler. M2 could be a milling machine, let's say. Okay, so what I want to do is I want to start the oiler, and I want to make sure that the oiler runs before the milling machine runs. Okay? So I start the oiler and it latches up. Okay, this would be my M1. And then my M1 contact, normally open, would also start the milling machine. Okay, now how do I know the oiler's working just before the milling machine comes on? How about a safety? How about a safety? So for a safety, I'm going to close an oil pressure switch. So now, when I hit the start button, the oiler starts, it latches, and it also closes this rung. But until the oiler builds up oil pressure, the milling machine is not going to start. If I lose oil pressure, the milling machine will stop. So I've always got oil on the milling machine for it to run. Okay, now this is another convention. We call this an interlock. Okay, it's like when we learn logic, when I was in school, we talked about if, then. If the milling machine is running, then the oiler is running. Okay, so it's not just a drawing anymore. It's actually a graphic representation of a sequence of operation. Okay, now sequence of operation is a very it's a general catchphrase for any system that you control that has to have one thing happen and then another, or variable inputs. I'll give you an example. I have a building that's occupied during the day. I want it to be heated while my employees are in there, okay? If the temperature in the building is 70 degrees, then the heating system doesn't have to work. If the heating system drops below 70 degrees during the regular business hours, say 8 to 5, then the boiler fires, I circulate hot water through fan-cooled radiators, I heat the building. I use thermostats and other sophisticated temperature controls to maintain that temperature. However, I don't want to heat the building warm and toasty on the weekend or at night when there's nobody in the building. So all of these parameters go into what we call a sequence of operation. And the sequence of operation ultimately will be represented in a series of ladder diagrams. So this is how we take a graphic representation and turn it into what we want to have happen when we run machines, systems, and so forth. So when I talk about conventions, I'm talking about typically interlocking, jog run, and sequence of operation. So I hope that helps to clarify. Our next video is going to move on from this point, and if anyone has any comments or questions, please let's have some feedback right here. Thank you very much.